Hello and welcome. My name is Nordling and I'm an assistant professor in mechanical engineering at the National Shengong University in Taiwan. I'm also the general chair of this workshop. Now, behind me I have the Department of Geomatics. It's my pleasure to introduce our honorary chair, Chair Professor Wu, which will give his welcome address.
It is a pleasure to welcome all of you on behalf of the National Shengong University in Taiwan. I'm proud that our team, the NCKU Parkinson's Disease Quantifiers, are one of the finalists in the OpenCV AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OAK-D camera together.
Hello and welcome. I am Akram Ashiani, postdoc researcher at the Department of Mechanical Engineering of National Shengong University in Taiwan and assisting chair of this workshop. It is my honor to introduce Mr. Jay Shah, a PhD student at Arizona State University and machine learning podcast host. He will give a presentation on explainable artificial intelligence, including lessons learned from being a podcast host.
Hello and welcome everyone to whoever is attending this workshop. I am Jay Shah and I'm a PhD student at Arizona State University. And today I'll be talking more about the landscape of interpretable AI and my learnings from hosting an ML podcast. Most of my projects are being funded by Barrow Neurological Institute, Mayo Clinic, and Banner Alzheimer's Institute in Arizona. The outline for this particular talk for the workshop would be I'll be talking a brief introduction about my background and what are the projects that I'm working on, a brief introduction to what explainability versus interpretability really mean. What is the landscape of explanation methods? What are the methods out there and what are the limitations for each of these methods? And we'll look at a glance of what Shapley values mean, which is a very popular technique for explaining deep learning predictions. We'll be talking about what lies ahead for this particular domain. And lastly, I'll be concluding my lessons from hosting a particular podcast that can be useful for any new young researcher or engineer out there looking for new domains to explore. So talking a bit about me, I started my undergraduate study at Dhirubhai Ambani Institute of Information and Communication Technology in India in 2014. And during that, I visited NTU Singapore, which is the Nanyang Technological University in Singapore, where I worked as a visiting research assistant on a 3D point compression management algorithm project, which was a research grant based on from the university. And post that, I also interned at HackerRank in India, where I worked as a machine learning intern trying to learn more about the data pipelines of how to create reliable machine learning pipelines for data analysis and real-time platform management. Post that, I graduated from my undergraduate degree in 2018 from DIST in India. After that, I joined Arizona State University here in United States in 2018 for my master's in computer science degree. Followed that, during my master's, I was fortunate enough to work with Professor Frank Wilczek, who is a Nobel Prize winner in physics. And I explored with him the idea of using machine learning for art authentication tools. It was a research exploration project where we looked at novel techniques for classification of real versus fake pigments. And starting from colors to different substances, we were able to make a tool that can authenticate if a painting is a fake or not. After that, I interned at the Philips Research Labs in Cambridge in Massachusetts over here for a medical imaging project where we were trying to build a contactless patient monitoring system for their vitals measurement and their heart rate systems. And this was primarily to be used for ICUs and NICUs for small babies who cannot be operated and cannot be contacted with any equipments. Post that, I graduated with my master's degree in 2020 from Arizona State University. and I joined the PhD program at Arizona State University with a focus on working in medical imaging. So right now, most of my projects are being jointly funded by Mayo Clinic, Banner Alzheimer's Institute, and Barrow Neurological Institute within Phoenix here in Arizona, where I'm working on total of 3 projects, from which the first 2 are the most primary ones that I'm currently working on. And one of them is post-traumatic headache, which is a common neurodegenerative disease where a lot of people suffer from this particular disease. And we are trying to look at a multimodal solution from a deep learning perspective. We are trying to combine different modalities of data to understand what are the mechanisms, what are the biomarkers really responsible for post-traumatic headache. I'm also working on understanding the underlying biomarkers for Alzheimer's disease, which is one of the biggest and maybe the most leading neurodegenerative disease across different populations of Earth. And we are also working on longitudinal studies of understanding how Alzheimer's disease really progresses for severe or mild patients and how we can track them down. We also have few publications that we will be publishing out, and few of them have already been published. And the one that relates to this particular talk is interpreting deep learning model predictions using Shapley values. And I'll be presenting more about these works in this particular talk and also at these particular conferences. And apart from this, apart from my curriculum, I host an ML podcast, which is supposed to be useful for students who want to get started in the domain of AI, ML, or in general, just the basics of computer science that is relating to research. And I have been inviting people from different backgrounds. They are working as research scientists, as professors, as engineers, or even as data scientists from companies like Google, LinkedIn, Facebook, NVIDIA, Microsoft, and talk more about their insights, what they have really to share, what they have learned from the industry versus what they wished they could have learned as a student. And I host this podcast on the various platforms so that people can have access to this particular platform. I also contribute to IEEE community, and I received the IEEE Impact Creator Award this very year in the starting of this year for my contributions to the IEEE community. I also serve as the technical director for AI Club here at Arizona State University. And apart from this, I have a list of other extracurricular activities. If anyone is interested to know, they can visit my webpage where I do smaller contributions to help people understand this domain better. On the basis that I have learned through learning from different peoples, talking to different peoples, and I normally post them in the best way possible. All right, so that was a brief introduction about me. Let's try to understand what is the difference between explainability and interpretability and why do we need it in the first place. So over the time, we have realized that the applications of machine learning has really scaled into various topics and domains. One of them and one of the most used is in medicines or in clinical settings, where doctors are using these AI tools to understand the data better, to have precision medicine, to have precision treatments. Over there, we have been really successful in using a democratized version of AI. Second is the legal systems. A lot of legal-based systems are using AI-based approaches to make decisions and predictions about the trajectory of any crime. A lot of people have also been using in financial trading to understand the patterns of prices of stocks and other variables that are responsible for financial trading using machine learning techniques. A lot of these recommendations that we see either for personal platforms like Facebook, Instagram, to Amazon and retail marketing shops where they are using and making a business-based revenue out of these products. And also in banking systems, where they are using these smart techniques to understand the risks associated with giving out loans or opening new bank accounts with high stakes. So basically, we can say machine learning applications are really becoming ubiquitous across all different types of genres of topics that one can think about. But why do we need interpretability? Like, what does it really call for the need for interpretability in AI? When we talk about these applications such as healthcare, which has high stakes, where where a slight change in the decision making process can result in a high amount of variance, high amount of risk, or maybe giving out loans, or let's say even the legal systems where taking risks on A or B could have a dramatic or drastic change into what are the consequences of that particular thing. This is where the black box models really lack these efficiencies. So we don't really rely on these black box models, even though the performances are good and the predictions are really crucial to understanding what is really going on into the model. And hence, the domain of explainability or interpretability of these models has really become critical, because we see more and more usage, but lesser and lesser understanding how these black box models are really working. But is that it? Like, is that the only reason why we really want interpretability? Well, once we start looking at what interpretability can provide, it really becomes much more clear. So, given a particular deep neural network, we see the end users. That is the real concern, right? We are concerned about people using it and not understanding it better. That is the concern. But apart from that, there are other reasons. When you see a lot of literature where people have pointed it out, for example, in this particular paper, they pointed out that an image with cat can be subjected to adversarial noise, such that the prediction could really come out for a dog. So this particular image was added to noise in such a sense that when it was downscaled, the prediction or the model was predicting it to be a dog. So that really means, like, how much do we trust these algorithms, right? Like, have they really captured the essence of classifying an object of cat versus dog breed or any kind of animals, or even for high stake, like let's say facial recognition? So how do we make sure that these algorithms have really understood what it means to classify? So one other point that really comes up with the idea of interpretability, if we can understand these models better, we can develop the domain of model debugging. So for us as programmers or researchers, we can have an arena where we can see and debug a particular model. But apart from these, there are other scenarios too. For example, you have a data set of a person in the legal system. You use a predictive model to to assess whether this person is risky to release or not. So this is a legal system. But while doing a quick analysis on these, we understand this particular prediction is biased on, let's say, the race or gender, and which is a wrong thing. It is not using any kind of logical approach, but just overfitting or maybe underfitting the data. So these kind of biases could be really predicted using these interpretable approaches. So we learn that, okay, these methods can really help us with bias detection. And overall, once we learn that how much unreliable these systems could be, we can speak about the reliability of models. When you are deploying these models, not in just your lab or just for your playful activities, but when we are dealing with these models in the real world scenario where actual people are at stake, we cannot really comment about the reliability of models. So how much reliable these models are. And once you start learning about these topics, two words that you will see a lot of in the literature or on the internet are interpretability versus explainability. And they are used very confusingly. A lot of people use these terms interchangeably, but they are not really meant to be. So interpretability in general means building inherent interpretability in general really refers to building inherently interpretable models. So we are talking about the model's internal structure, if it is interpretable or not. Versus explainability really refers to the idea on a post hoc sense. So you have the model, you have the complex non-linear model that is trying to make very good predictions. But what do I really make out of these predictions? So it is in the post hoc sense. That is, once the model is trained, what do I do to understand it better? So it refers to explaining the predictions better in human understandable sense. And as a first step forward, the way people have been approaching these idea of model understanding, The approach one is always the easier one, which is building inherently interpretable models. What do I mean by inherently interpretable models? We all have seen these models like linear regression and logistic regression, which are linear models. You can easily see and analyze the weights associated to all the features. They are fairly low dimensional for us as humans to interpret, understand, visualize, and we can see what's really going on. So if a model is predicting very nicely using these models, it's easy for us to interpret. It's easy for us to analyze what's going on. Or models like support vector machine, or even random forest classifiers, which uses a collection of a lot of decision trees, but we know what's happening towards for each of these decisions. But the approach two, which is the most popular one right now that you will be seeing, is explaining black box predictions. So what do I mean by black box? They are typically these highly stacked layers of deep neural networks that we are trying to optimize for the input and output values. And typically the way people go forward for this particular models or in general approaches is once the model is trained on the set of inputs and outputs, they will take these predictions, or rather I would say probabilities of all the feature classes, and try to use an explainer model or explainer technique that can explain something like, for example, in this particular photo, I'm showing the Shapley value results, which we'll be talking about in the later. But these kind of explanations tell us which features are really the ones that model is looking at. What are the significance of each of these features that the model has learned. So I'll be talking more about the word which is called post-hoc explainability, which really means is I don't touch the model that is doing its job perfectly, but I only try to use these predictions and the input data to understand what's really going on. But you might say, oh, okay, if that's so easy, why are not people doing that? Like, what's the big discussion about? The big discussion really comes in when we look into the infamous trade-off. You see this plot which has these various types of models, starting from linear regression, which is one of the most simplest models, to deep neural networks, which are the most complex models. And the trade-off that you see is the accuracy versus interpretability. So deep neural networks are highly accurate. They are performing and outperforming humans at times. And the accuracy is really nice. But the interpretability over here is very, very low. Not a lot of people are trying to understand that. And linear regression, which has a fairly low accuracy, but they're highly interpretable. So how do I choose? How do I get the best regardless of these trade-offs? So this is where rule of thumbs really came in. This is maybe a couple of years back, where people concluded that please use inherently interpretable model if at all everything is working perfectly fine for it. So first of all, analyze what is the size of data set that you have. What is the end goal? What do you want to do? If the performances are great, please use inherently interpretable model because of the reasons that I just mentioned in the previous slides. But let's say you really have to use black box models because your data set is small or your data set is highly non-linear. There are no real combinations or associations that you can really figure out using linear models. And that's when we resort to post-hoc explanations. So this was the brief story behind explainability and interpretability. Why are we talking about this in the first place? So now that we know what's the reason for that, let's dive into the landscape. What does the domain look like? So first of all, I'll explain what are explanations. What do we mean? Like, are these kind of a movie? Like, are we talking about paragraphs explanations? What do these explanations mean in the first place? So you have a model which is taking in this input and input and predicting the outputs, or maybe making predictions for each of these classes. We are typically looking at explanations using interpretation methods, sorry. And these explanations are normally tailored for the end users trying to use these predictions. So Normally, the task is to generate explanations only specific to the people who are concerned with the usage of these models. So in case of a healthcare, they are the medical experts. Or if it's a general app that you use on your mobile phone that anyone can access, then it's the general customers. So the idea is that these explanations should be human understandable. Yes, they should be true to the model's working. They shouldn't be faking up stuff. They shouldn't be lying about the explanations. They should be true to what model really means, and reliable, as in they shouldn't be just easily fooled, as in if an attacker wants to attack the system, it shouldn't be compromised. So such kind of attacks. Let's talk about the interpretation method categories. There are two types: model specific, model agnostic. Model specific are the ones that are built for specific models, specific types. Whereas model agnostic are the kind of interpretation methods that are present for all kind of models. They are not really specific to any kind of models. And the explanation categories. So we have these local explanations that will just take one prediction, one data sample, and try to explain why the model predicted that particular value, versus global explanations that will try to comment on the overall model's training, as in what is the model trying to learn, what is the overall idea of that particular model's learning. Now let's take about the example of what are the methods. What are the methods available for each of these categories that we have been talking about for so long? So the methods that have been really developed for local explanations, taking one sample and producing outputs or maybe explanations for that particular data sample. One of the most popular ones that you will see that are feature importance based methods. And one of them is Shapley, which is a game theoretic approach. SHAP really stands for Shapley additive explanations. And the idea is very simple, even though it sounds very complicated, but you have these features, you have these predictions. You remove one feature and train them, you remove one feature, you use the remaining features to make a prediction. And so on and so forth. You try to remove and put them back. You try and remove all of these features. And through all of these permutation and combination, you try to see which feature is really important, which one made the real difference. So for n features, you can assume there are n factorial of combinations. And for all the instances, you do that every now and then. And so this is a game theoretic approach where people are trying to remove and replace these features and understand what is the importance of that feature. If by removing it doesn't really help, then it's not an important feature. And this is the way people are really learning that, okay, in this particular case, the one that has the red dots on a lot of regions is the most important one. So this is a SHAP summary plot where you can see the first feature is really, really important for that particular classification. Another popular one is LINE, which is local interpretable model agnostic explanations. And you will see the performance of these particular techniques a lot better than the other ones, because it's fairly very reliable to use in some senses. But we'll be talking about limitations later on. But the idea is very simple. You have the data set, you pick the one that you want to explain the prediction on. You pick that data sample and then generate a sample data set around that particular data point. So you pick a sample DI and generate perturbations. So these are the artificial data set that you generated. You predict for each of these data samples and see which one is really making a sense. And you try to weigh the samples, and then you make an explanation that, okay, these features look like this, or this particular data samples look like the other ones, and so on and so forth. And you use a simple linear model to make these explanations, of course, because you don't want to train a very complex model on top of a complex model. So these particular models have local fidelity. They can really talk about a particular sample in its neighborhood space, but they cannot really comment about the overall data space or data cohort. So these are one of the limitations of these particular models. And you will also see in literature a lot of people calling these linear proxy models, where you try to proxy this particular complex model with a simple linear model. Counterfactual based explanations, which is where you have a person who is trying to request, let's say, applying for a loan, and the bank is using a predictive model and it rejects the person's loan. So the counterfactual explanation methods can really create these explanations where if the person has a question why the loan is being rejected, the person can have an answer that if I had an income more than this, I would be approved this loan. So this is kind of a counterfactual explanation trying to help the user understand what's really going on with the model. The other one is the instance based, where prototypes and criticisms based. Prototypes are the kind of representative data samples from the data cohort, and criticisms are based on that are not a part of the representation of prototypes. And influence based are you try to find the best instances that are trying to influence the predictions. So you pick out these very, very simple instances from the overall data sample and try to explain what's really going on. What are the samples that are really making an influence or influence in the prediction process of these models. And saliency maps, one of the most common ones that we see with imaging data, computer vision techniques, is you have these images which are making these classifications. You want to learn what is the model looking at, right? In this case, I want to learn where is sheep and where is cow according to the model. And you see these kind of outputs where you can really verify if that is really the case. But global explanation based, now I want to learn about the overall understanding or overall idea of the model. I want to see what is the idea. So one of the most popular, I would say, technique that was developed by Google, which is the concept based technique, where you see, for example, in case of a zebra, you want to understand how much is the importance of black and white stripes really going on for classification of a zebra. And you try to train a linear classifier on separate activations. So you create these different kind of activations and try to see. And the paper that was published, it really says that the vector orthogonal to these kind of decision boundaries that you build using a linear classifier are really what the model understands as concepts, or in this case, let's say stripes. So a vector orthogonal to these decision boundaries really refers to the stripes in that particular data set understanding. So gradient with respect to this vector will tell us how much important these particular stripes are for the classification or the prediction in this case. Proxy models. So you have these black box models which are doing perfectly fine for input data and trying to create these labels. But instead, I try to explain or maybe proxy these things with a very simple based models. So I will try to create a model that can mimic the same predictions, of course, by a certain extent, not the same, but I'll try to create a model that can mimic the best. And because I know these models, I know how interpretable these models are. So hence I can make a prediction, which is not really effective. But again, it's a classic way of getting away with the idea. And aggregating local explanations. So we talked about SHAP and LIME, right? They are using each data instances to explain things better. In this case, we try to aggregate them. So methods like SP-LIME, which are trying to make an aggregation of K explanations that are choose very greedily based on the behavior of that model, and they will try to combine all of these predictions explanations to comment about the overall idea of the model. And SHAP also provides a summary plot, which was later integrated into the module, where it can really comment on the overall idea of the model. Something like this, where it says it can comment about all the points in the data code. So these were the different methods. I'll be quickly jumping to the limitations because these methods are not perfect. They are recently developed. So the idea of the domain of research is really, really naive. And one of the biggest limitations are these two particular points. First, the truthfulness of these explanations. Are they really true when they give us these explanations? How do we verify them? And there have been few papers where they are taking a review-based approach to understanding if at all these explanations are good. And we see, for example, in this particular case, you see all of these techniques which are trying to make an explanation, but at the end, if you see, it just resembles an edge detector. The outputs look just like an edge detector. So how do we really know? In this particular case, the second one, where the girl is eating a corn, It's trying to basically do an edge classification or edge detection rather than actually commenting about the girl or the con or the background. So we don't really know if at all these explanation models are picking up what we really want. So we have to be really careful how much truthful these models are. And reliability, talking about these things, one of the papers that I'll be linking in the references later on is trying to learn when we say Lime are creating the perturbations of data samples around the picked data sample, these really lie outside the data distribution of the data cohort. And because these explanations are based on these perturbations, if the perturbations are wrong, that means the explanations are wrong. And that means the explanations are not really talking about the model itself, but based on some random pattern of these perturbations. And this was one of a very highly cited paper where people are trying to investigate what's really going on at all, if we should be using these methods like Lime and Shep, because they are highly inconsistent. And also these kind of images where if you provide noise or adversarial noise to these kind of images, it can create different explanations. I mean, something like this of an explanation can be changed into something that we want, is something highly manipulative. If the methods are manipulative, they are not reliable. So reliability and truthfulness are some of a bigger concern over here. And since a few of my projects, I have been exploring the application of Shapley values onto my own data sets. I'll be quickly explaining what do we mean by Shapley values. I'm sorry. So as I mentioned, I have been working on these three projects. One of them is post-traumatic headaches, where I'm trying to learn the idea of what really contributes to the classification of post-traumatic headaches. And an approach I want to take is multimodal deep learning model. And even just one modality of classification really brings in so much complexity while using deep learning models. The idea of using multimodal deep learning models would be something magnitude of inexplainable, right? So that is the reason I want to work on interpretable AI models or explainable methods in order to understand what the deep learning model is really learning and really telling. And a brief idea about what are the post-traumatic headaches and what is the research problem. Why is it so much interesting to me? The problem with post-traumatic headaches is it's highly heterogeneous in its own self. So two people can have the same brain injuries, yet one might get PTH and one might not. So we don't really know what really contributes to having a post-traumatic headache. What is the reason? What are the biomarkers? And it's a truly multivariate study. We cannot just look at an MRI scan or a CT scan or just blood biomarkers or plasma biomarkers to understand. We really have to make a consensus among all of these biomarkers at certain point, and also including the demographics of a patient. And thirdly is the exploration of AI in headache community, wherein the medical research is very, very limited. So no one knows really what data to collect, what to process on, and other details. So the goal is to use deep learning to find biomarkers across modalities, either combined or separate. So that's an open area of research. The data set that I'm using is an in-house data set, so I cannot reveal all the details about the data set, but these data sets are based on an NIH and DoD funding for post-traumatic headache and migraine patients. And we have these three modalities: clinical data, imaging data, and speech, as in the audio features that are collected from an audio app on the phone. So a lot of people have a confusion of how Shapley values really work. So I've created a very simple explanation in case that really helps. Let's say you have a company where you have two employees. One of them is me, Jay, and there is a friend of me, John. If no one of us works, the profit of the company is zero. Let's say if I'm only working and the company makes 20 units, that means my contribution is 20. Now, if only John works, the company earns and makes a profit of 10 units. That means John's value or contribution is 10 units. But if we both work at our full potential, the company is making 50 units. The question is, how much do we each contribute? Like, what is the pay that we would get? What Shapley value really does is it takes all of these combinations. So let's say if I am the one, this particular permutation where I'm the first and the second is John. So we already know I have the potential of 10, 20 contribution, 20 units, then we can guess that, okay, if the total was 50, and given that my contribution was 20, John would have contributed for 30 units. And for the other permutation, we can do the same thing where we can say Jay would have contributed for 40 units. And we really take these averages for this particular Shapley value. So on an average, it says that I contributed to 30 units, whereas John contributed to 20 units. And this is the idea of SHAP in itself. We had two features over here, and that's why the permutation and combinations were limited to 2 factorial, that is 2. But in case of an n factorial, you can imagine how much long it could get. So the way a lot of people ask questions is how can we connect Shapley values with deep learning is we have these idea where this black box model can be represented with these kind of explanations where what it really means is something else. And the model that we have been using is a data-based model where we have data, a neural network, and the probability values across different classes. But instead, what we do a classification, not just a standard classification pipeline, is we use these explainer techniques to understand what's really going on. And we have these outputs like these. Where we really learn about what are the contributions for each of these features. So the red ones are the ones that are contributing positively towards the classification, versus the blue are the ones that are contributing lesser. And I'll be skipping these slides over here because I'm running out of time. But what it really shows is SHAP is really, really powerful at capturing some of the minute details that neural networks typically might not have captured. For example, this particular case, which was supposed to be healthy, but it really truly classifies that that particular patient has post-traumatic headache using these kind of Shapley value plots for each data instances. So we really learn what's going on wrong with this particular PTH number 22 patient, and we really see what is the feature really responsible. So what really lies ahead? What's the future for any young researcher? The domain is fairly new, so a lot of things are lacking. The definitions, the robustness, the reviews for these methods are really missing. There's no one silver bullet. We cannot have one method that explains all. It's really specific to applications. It's really specific to the problem you are solving and the method you are using. So it varies a lot. A lot of the research you will see will be focusing on post-hoc explainability of these models because of the inherent love for a lot of people using deep neural networks. So the research community might be focusing on post-hoc explainability a lot. The focus would be on robust explainable systems because these have a clear understanding in the industry. A real application based demand would be in the industry, and hence I think robust explainable systems would be something really an important feature. And lastly, and metric to evaluate. Once we have these models, these beautiful techniques that can explain, how do we really evaluate them? Like, how do I make sure this method one is better than the other one? So we at least need to have metrics, or at least to some parts of that particular model. And lastly, about something off topic, that is my lessons from hosting a podcast. I have been hosting these podcasts where I have invited more than 30 or 35 engineers, professors, research scientists from very diverse backgrounds. They are in academia, they are in industry, they are in the engineering domain, startups, even news reporters, and a lot of people working within the domain of ML and AI. And the goal is to learn what they have really learned as their experience of either a PhD student or a master student or an undergraduate student, or being in their research roles in the industry. And few things that I've learned for myself while interviewing these people is I have learned that few things, if I were to note down or maybe summarize based on my interaction and all of these podcasts, the first goal that they try to focus on is hands-on experiences. Whenever I ask them, how did you get started, what tips you would have for people who want to get started, is the number one advice is hands-on implementation. Just think about it, Just go ahead and implement a model. Either it could be just copy pasting from Stack Overflow or Medium articles. Just go ahead and implement. See for yourself what the model is doing, the way it is doing. Change these data sets, see what it does. Learning the differences between theory and applied AI. A lot of people are intimidated by the mathematics that really fall behind these AI applications. Learn what interests you. Is it theory? Then go for it. But is it applied AI? Then you can take steps accordingly. Try to learn what is the impact of this research. Like that will really motivate you and give directions as to where to proceed ahead. Benefits of networking are highly underrated. Like just go ahead, talk to people, talk to different domains of people, not necessarily computer science. You will get new ideas, new motivations, new general overall ideas to work on something interesting. And reach out more, ask questions. Even though there are high chances all of us have the same questions, we might all be stupid enough to ask these questions. So yeah, don't be afraid to do that. And yeah, feel free to check out these podcasts in case these are useful for you guys to get started or maybe learn about the basics. And reach out to me if you want, because these podcasts are really meant for students and young newbies who want to get started with the idea or with the domain of machine learning. So yeah, hit me up with any kind of suggestions, comments, questions. If you're feeling stuck about how to get started, hit me up on my homepage, or I'm always up for a chat on LinkedIn or my Twitter accounts, as I mentioned over here. But thanks a lot for attending. I'm fairly over time, but I thank you all for attending this workshop, and let me know if you have any questions in the chat section below. Thank you.
Morning, Mr. Shah. Thank you very much for the great talk. I'm your host of Q&A session. We have put the link for our Google Meet in the chat. So for audience, if anyone want to join, please feel free to click it. At the same time, let me read the question in the chat for you, Mr. Shah.
Sure.
Okay, so the first question in YouTube is, should financial credits and insurance price depends on AI? Or do the people have the right of a model that can be explained even if the AI is better?
Yeah, I think people do have the option. People do have the control of what really the model is doing. It's normally a tool for us to help if at all the model is doing something wrong or not. But I think even for critical scenarios, we as programmers or researchers have to really make sure that we are not in a fully automated process, right? So we are just aiding the people who are the experts, but we are just making their life easier. But I don't see a thing where people are just solely relying on these kind of tools for the ultimate decisions.
Thank you. Next question is, what is your personal opinion about ethics and how much a model can be explained?
Yeah, I think for ethics, it's like more of an open debate, like because the coverage for ethics is really huge, so it's hard for any one of us to comment. But for my understanding, I think ethics has to really deal with the biases of data. So when model is making any predictions, we have to really make sure if the biases are not present, that is discriminating for unknown reasons, or at least known reasons, but they are not right. For example, in one of my presentations, I did mention about parameters like gender, race, or ethnicity, which is highly wrong if at all we are making a fair prediction. So I think by ethics, I really understand these kind of scenarios. So we have to really tackle that. Those kind of ethical issues are covered. And I assume there was a second question. Can you repeat that? I think you did
Yes,
mention
the
something.
second question is, how much model can be explained?
Yes, for now, like as of now, I think that's an ongoing field. So definitely it's down the line 5 to 10 years, the models might be explaining themselves better. But for now, I think we are at a very naive stage. So like I said, like models like SHAP and Line, they are explaining a bit good enough, so I can understand what's really going on for that particular prediction, but it's subject to a lot of adversarial attacks. So it's very wrong for me to comment that VR models are explaining completely, but at least slowly the research is moving forward, that people are making efforts so that at least some parts of the models are being explained. But I would say that's still at the surface level. We are not going down the surface for understanding these models.
Thank you very much. Next question is, AI work based on the data feed for training. If the training data is biased, the result will also be biased. Is there any method to detect or recognize such bias before start training AI?
I think yes, there are lots of data pre-processing techniques which actually makes sure, for example, starting from the very basic ones, right? Like not even the biases, but for example, class imbalances or understanding the demographics. For example, because I work with a lot of healthcare data sets, we always make sure that demographics, for example, ethnicity, age distributions are always brought out. We just don't have a particular age set of people. Let's say if I'm just taking MRI scans or clinical data from only one small group of ages and then trying to test the model on different age distribution, that's a very wrong thing, right? And similarly, if at all you are using it for different ethnicities, we have to really make sure that if the distribution is nice enough. So we have to for at least and I assume even for other domains too, but at least for healthcare, we normally make sure that the data is evenly distributed, or like we said, generally distributed. So there are not many fancy techniques. These are just basic statistical techniques that people have to really make sure, and they are a part of data pre-processing pipeline.
Thank you very much. There are also two questions from Twitch. The first one is, for shop, do you remove the feature one by one? What if I remove two features or more at the same time? Will that make some differences?
Oh yeah, so SHAP is normally taking, I just gave the example of removing one feature, but SHAP actually does it for all the N features. So it will remove one feature and then maybe put it back and then remove second one. But in the next iteration, it will remove two features and then put two back. So it's more like an N factorial thing. So the way we understand probability, right? So there would be N factorial possibilities. For each of these, we have either we put it or we remove it. So there are N factorial possibilities. So yeah, we whatever combinations we as humans can think of, it will do all these combinations, make predictions, and take an average. Or there are different ways of average is just one of the ways combining these predictions, but average is a common technique that Shapley uses. But yes, to answer it, it also removes two features, three features, till N features. Yes.
Thank you very much. The next one is so far the last one. So if audience want to ask more questions, please just feel free to put in the chat. So the question is, we know that a gray box model is a combination of black box model and white box model. In other words, adding the physical or theoretical meaning into the model. Is there any gray box model in machine learning field?
I'm not really sure. I'm gonna do a guess over here for answering this question, but at least for the statistical based machine learning techniques where we have handcrafted features, right? This was maybe a few years back when for a medical or healthcare problems, they would process these features or MRI scans, but they won't be using these images, but they are highly selective. Let's say only ROI based techniques, right? If people over here listening to this podcast might know, is ROI based techniques where they will only input the interesting ROIs and then train a maybe simple machine learning model, just like KNN, K nearest neighbors, K means algorithms, or something like that. So maybe I'm not really sure the exact definition of gray box models in machine learning, but if at all that would be the thing, because you have a control of what features you are inputting. You are only inputting the important features. So maybe they do exist, but they have been outperformed by deep learning by many different scales. So that's the reason I don't think so they are very relevant. But yes, if at all, but I could be wrong. So yeah, I'm just taking a guess over there.
Thank you very much. So since we don't have any more questions now, I think this is the end of today's Q&A session. Thank you so much for the answer. Also, we will have another workshop at tomorrow 2 p.m. and hackathon at tomorrow 4 p.m. For more information, we have already put the link of our website. Please take a look. Look forward to seeing all of you. Thank you, everyone. Thank you, Mr. Shah.
Thank you. Thank you very much. Bye-bye.
Bye.